Okay, I hope that you have gone through the last two classes carefully. If you have not gone through them, then you should first go through them and then come back to watch this video. The last class was about the introduction to cosmology, and the class before that was about how do you, what is about special relativity. So, both of these ideas will be useful today in this particular lecture. So please go through them first and then come back here. So what we'll discuss today is more about Hubble's law in a certainly more mathematical perspective than what we discussed in the introductory class. Okay, so let us start. So what was Hubble doing? So he was certainly doing observations and or interpreting observational data. So what are those observational data? So let me write down the observational data first, what they were observing first, because that's how you understand things. So they measured distances to nearby nebulae and so they called them nebulae because they did not actually know what they are. But so was the first person to point out that there are actually galaxies like our galaxy outside. So let me write just galaxies here. Okay. So they used the method of circuit variables to measure these distances. I think this was discussed in the last lecture, the introductory lecture. So it's a class of distance measurement is called luminosity distance measurement, which we'll come back to later in a later class. What is meant by luminosity distance? But the other thing they could measure, so they measured redshift. To the nearby galaxies, the same galaxies they were observing. Okay, so let me tell you, let me show you one and try to make you understand one of the modern day measurements of the redshift to the galaxies. The luminosity distance measurement we have already talked about. What is luminosity distance? How it is related to things that we'll discuss today will be talked about in a later class. So what you see here is the spectra of one of the nearby galaxies. The galaxy position is written over there, and so some certain other numbers written, which is not of importance for us. This is measured by the SDSS Sloan Digital Sky Survey. Uh, this is a part of that measurements. So what have they done? They look at the spectra of the galaxy, and when they look at the spectra of the galaxy, they see these spectral lines. So first of all, a galaxy spectra is nowhere near to a black body spectra like for the stars, but it has a continuum, which you see here. So that's a continuum. And on top of that, you have these spectral lines. So the lines that you see with lines, those are marked by those vertical lines. So these are there. So then what do? You note down the wavelength which is in the x-axis for all of these lines. So the wavelengths you note down for all of these lines. So wherever you have a line, you note down the wavelengths, and then you ask the question that what are these spectral lines? Where are they coming from? Like for example, if I look at say this particular line, which transition, spectral electronic transition is causing this line? Like for example, it's talked about the hyperfine structure transition in hydrogen atom, that was an atomic line, but most of the lines that we know of happens because of transition between two electronic levels. Though what are those? And that they have identified and marked here. So each line they know exactly where are they coming from. So what are the original spectral line. Now how to do that is a little complicated, so I will not go into that. But what happens, I can show you. What happens is the following. So this is depiction of the spectra of a galaxy, and you see that they have purposefully written in different, given it in different colors, and you see there is some striking similarity between these spectra. So every time you see these, you observe that there is a shift in the spectra, right? So this line, for example, has moved there and then there and then there and then there. This line, for example, has moved there and then there and then there and then there. And you can see the amount of shift is different at different uh, places. The shift is more here compared to the shift here. But at least if I know that what are those lines, so all of these lines, if I can identify, I'm just pointing them out in the lowermost spectra, then I will be able to find out, if I look at this spectra, then if I look at this spectra, then I will be able to figure out that what are those lines in the red spectra, or vice versa. If I look at the red spectra and I know about the blue spectra, then I will be figure out where are these lines in the red, what are the lines in the red spectra from my knowledge in the blue spectra. And that is the idea, that once you know that, you realize the following. You realize that the lines, or Hubble realized that the lines are all redshifted. What do I mean by redshift? I mean, if I consider that the lines are observed at a wavelength of lambda observed, and the original wavelength of the line when it was emitted is lambda emitted, then the lambda observed is more than lambda emitted, and the redshift is defined this way. So that's the definition of the redshift. And it's called redshift because if the observed wavelength is more than the emission wavelength, then Z is greater than 0. Okay. So that's what they observed. That's what Hubble observed. But that's not all the observations. Now, Hubble is looking at the galaxies at different redshift. When he saw that these galaxies are redshifted, the spectra from the galaxies are redshifted, he tried to figure out why this can be. And one reason for redshift, he thought, so Hubble thought, reason for redshift is that the galaxies are moving away from us. Okay, so if you think of that reason, so then so the galaxies you can think of are moving away from us with a velocity v, and this velocity divided by the speed of light he interpreted as redshift. So if I know what is my redshift, I can get this velocity, just multiply z with c. Okay. So remember, now with this interpretation, he had two measured quantities. So he had two measured quantities. The velocity and the distance, right? So he plotted velocity versus distance, and this is his original plot. So in the x-axis, the plot is not very, the resolution of the plot is not very good, but you can see distance over here, and you can see velocity over here. These are in kilometer units, and these are in parsecs units. So there is 10 to the 6 parsecs. So these are basically megaparsec units. So it's 0 megaparsec, 1 megaparsec. He could go up to 2 megaparsec. And you can see, if you don't draw these lines, they are kind of scatter plots. But Hubble drew this line, and he found out that the velocities are proportional to the distance. And he figured out the proportionality constant just by fitting this straight line. And he, I don't know whether he called it, but we call it Hubble's constant. So we write V equals Hubble constant times t. So this is the distance that was measured. The distance is the direct measured quantity, remember, and this axis is the velocity. The velocity is inferred, so the velocity is inferred as c times z. And when he plotted for all these nebulae, so this dot circles and the points are all nebulae, don't try to ask the question at this level, what are these circles and what are these field circles and open circles, why there are two lines, etc. This plot has historical importance, but the present day the plot will look quite different. But anyway, so when he plotted the distance versus the inferred velocity, he found that the velocity is proportional to distance, and the proportionality constant we call Hubble's law. So this is V equals h naught d. So let me write down what they are. So V is coming directly from here. D is measured by luminosity distance. H naught we call Hubble's constant. Okay, roughly there are very precise values of Hubble constant as measured today, but roughly the value is 70 kilometer per second per megaparsec. And you can see immediately from Hubble's plot why is this peculiar unit, because velocity is measured in kilometer per second and d is measured in megaparsec. So h naught has a unit of, kilometer per second per megaparsec. Okay, so that's Hubble's observation. And remember that the fact that the distance is proportional to velocity actually comes from the fact that the distance is proportional to the redshift. The proportionality from the direct observation, the proportionality is actually redshift versus distance. This is the actual measured proportionality, which Hubble interpreted as velocity and distance. Okay, so let us Go back to what Hubble observed once more. So they measured the distance to the nearby galaxies and they measured the redshift to the same galaxies. The redshift is defined as the shift in the spectral line observed minus emitted wavelengths divided by the emitted wavelength. So this is a dimensionless quantity. Redshift is a dimensionless quantity. And Hubble thought that the reason for the redshift is that the galaxies are moving away from us. So he equated redshift with V by C. So V came out to be C times Z. And when he plotted this V with the luminosity distance, he got this relation. So let me keep this relation in a little better form because this is what is the crux of the story so far. So the relation is V equals H naught times B. And the actual relation, if you remember, as we said, is Z is proportional to D just because V is the inferred velocity using this formula. Okay, so what we will try to do next is try to understand where this proportionality comes from. Is it really that the galaxies are moving away from us, so that is the reason for this proportionality, or there is some more uh, interesting reason for this proportionality? So it turns out that it is not that the galaxies are moving away from us. The actual reason is more interesting, and that is what we are going to learn today. Okay, so let us start. Let us start by revising. So I will complete this discussion here and will revise our discussion on special relativity. So again, if you have not gone through this special relativity note that I have shared with you, please go through it first and then come back to these discussions. If you don't, then you will find this a little bit difficult to understand. Okay, so what about special relativity? So first, one important thing we learned about special relativity is the concept of interval, or we called it also space-time distance. And loosely speaking, it has also another name, which is what we will call it by for quite some time from now. So it's called metric. Metric is not actually the distance. It's something that let you measure the distance. But for this discussion, we will use metric and interval synonymously. So what is that for the special relativity? Remember that we write it as ds square, or before we go to ds square, let me remind you what it is first. So we have two events happening. So event 1, every event happens at certain time, and say that time is ct1. And remember that for time coordinate I always multiply it by c just to make sure that it has the same dimension as the spatial coordinates, and this happens at x1, y1 and z1. And I consider another event which is happening at, you can imagine, all suffix 2. Interval is a way of measuring the space-time distance between these two events, and we'll not go through why it is so, and I have given a reference to look at to understand why it is so if you really wish to. But if these events are infinitesimally separated, means that T2 is like T1 plus delta T, X2 is like X1 plus delta X1, and so on, then we define the interval in the following way. And you see, if I take minus 1 common from this part, this is just dx square plus dy square plus dz square, which is nothing but a spatial distance between the point x1 and x2, y1 and y2, and z1 and z2. So the spatial distance can be written in a little different way. So this interval is in Cartesian spatial coordinates. If I write the same thing in polar spatial coordinates, the interval will look like ds square equals c square dt square minus dr square plus r square d theta square plus r square sine square theta d phi square. This type of thing we have seen before when we are doing coordinate geometry for the celestial on the celestial sphere. In that particular case, dr square was 0, but here we can have all of these. So this is in polar spatial part is in the polar coordinates. So this is Cartesian, this is polar. Now, for today's discussion and many discussions to follow, we will only discuss about cases where we have radial trajectories. Only radial trajectories. So what do I mean by only radial trajectories? I mean that, well, so when I say that so when I say that this is one event and this is another event, so maybe I mean that there is a particle which was at T1, which was at x1, x2, x3 at the time T1, and then it goes to x2, x1, y1, z1 at the time T1, and it goes to x2, y2, z2 at the time T2. So it's essentially you are looking at the trajectory of a particle, and in this particular case all x, y and z coordinates changes. But when I say a radial trajectory, the particle moves in such a way that for the radial trajectory, the theta part doesn't change and the phi part doesn't change. So only the r changes. And obviously the particle, if it moves, the time has to change. So for the radial trajectories, I will get ds square is c square dt square minus dr square. Right? So that is should be clear to you that for radial trajectories, I will not have any change in theta or any change in phi, and because of that, I get ds square c square dt square minus dr square only. Okay, so now let us so let me just rectify those mistakes that I have done while removing part of the notes. Fine. So this is what I have. We should also remember what happens for the case of a photon. But okay, so let us come back to a little later. Let us discuss a little bit about the space-time diagram that we had before, and we will only talk about radial trajectories. So ds square is c square dt square minus d phi square. Minus dr square. Now, how do I draw a space-time diagram? Well, we chose to draw the x-axis as the spatial coordinate, in this case r, and the y-axis as the time coordinate, obviously c times the time coordinate, so c dt. So that's where everything in the universe happens. All radial trajectories in the universe will happen in this diagram. So if I consider an event, say E1, which happens at CT1 and R1, so I don't need theta and phi here, so I have only one spatial coordinate. So if it happens at CT1 and R1, so that means that R has a value at R1 somewhere here, and T1 is somewhere here. So this is the point which corresponds to that event E1. If I have a particle which is kept at r equals to r0 at t equals to 0, so that particular point, that particular event is this. And if the particle doesn't move, the particle stay at r0 as the time progresses, at other times the particle will be found somewhere there where the r0 coordinate, the horizontal coordinate, the spatial coordinate doesn't change, but vertical time changes. So this is a line over which all the events corresponding to that particle which is kept at r0 will happen. So this is called, so this is an event. This is the world line of a particle at r0, and with, so what is the velocity of the particle? 0, right? Because it is always at r0, it doesn't move. 0. Now imagine that there is a particle which moves. So say the particle was at some place r2 at t equals to 0. So and it moves with a velocity v. So what will happen after a time? Obviously, after a certain amount of time, say at this time, so at this time, the particle would have moved, would have gone to a larger radius, because larger value of r, because it has a velocity, as I said, and the velocity is along positive at r direction. R is cannot be negative, but anyway, so the velocity has to increase. So what do I mean? I mean that the particle will be somewhere here. And again, if I try to draw the world line of that particle which has a velocity v, it will look like this. So this now corresponds to world line of a particle with velocity v. Okay, so the particle have a velocity v. Now, if I ask the question that what is this angle? So let's try to figure out what is this angle. Okay. To figure out what is this angle, let us start with our good old metric. So the metric is saying that ds square is c square dt square minus dx square, right? So let me keep it here, it will be useful shortly. Now the particle has a velocity v. What is what is v by definition? If the particle goes to a place r2 plus delta r from a place r2, and at the particle is at r2 plus delta r at a time t plus delta t, or t2 plus delta t2 from the time t2. So the particle is at t2 at r2 and then goes to r2 plus delta r at t2 plus delta t. Then that is the definition of the velocity, right? Now, for our example, so r2, the particle is at r2 when t2 is 0. So this is r2 plus delta r minus r2 by delta t, right? So if I multiply or divide both sides by c, so I get v by c equals to this. Now let us look at the figure. So in the figure, so say, just for the sake of understanding, let's say that here the time is delta t and the corresponding shift in r is delta r. Okay. So clearly in the figure, c delta t by delta r, c delta t is this much and delta r I have marked here. So c delta t by delta r is nothing but tan theta, and which you can see combining so what I have here is just the opposite of there. So tan theta is nothing but c by v. So I realize that this angle for the world line of a particle moving with a velocity v is always c by v, or tangent of the angle is given by c by v. Okay. So for the world line, of a particle with speed, and this is a constant speed v, of course, for this discussion. Okay, so now we'll look at the case for light. That is radial light rays. So what happens if I have radial light rays? So if I have light rays, what is this velocity of light? The velocity of light is nothing but c. So for light rays, tan theta is c by c, which is 1. So theta is 45 degrees. So if I consider a light ray, say starting from origin here, so I draw it with a dashed line, so that light ray trajectory will be, or world line will be this. So this angle is now 45 degree. So this is radial light rays. Okay. And what happens to the interval? Okay. So let us see what happens to the interval for light rays. So I have ds square, which is c square dt square minus dr square, which I can write as well as taking dt square outside. I can write this as 1 minus dr by dt whole square by c square, and dr by dt we have already agreed is the velocity of the particle, or in this case light, that we are talking about. But let's write first v square by c square, and you immediately see that for light rays v is nothing but c. That implies ds square is c square dt square times 1 minus now c square by c square, which is essentially 0. So what have we learned? Doing all these radial light rays ds square is 0, which implies c square dt square minus dr square equals 0. So that is the take home message till now. So let us go back to our discussion on special relativity and revise for the time being. So we said in special relativity we have this concept of interval, or we call it spacetime distance or metric, which is the essentially the spacetime distance between two events E1 and E2, and that is given this way. When I write in terms of Cartesian spatial coordinates, but I can also write in terms of polar coordinates, where it comes out to be what is written over here. And then we said we will consider only radial trajectories, where d phi and d theta become 0, and we get ds square like this. We then discussed about space-time diagrams. One event is a point in this diagram. Trajectory of or one line of a particle at r equals to r0 and doesn't move with velocity 0 looks like this, and then one line of a particle with velocity v looks like this. Then we figured out that the angle that this thing makes for a world line of a particle with velocity with velocity v, that angle tangent of that angle is given by c by v, where c is basically the speed of light. And if I consider a radial light ray, then the velocity is also c, so tan theta becomes 1, theta becomes 45 degrees and ds square is 0.